Hello students, welcome. So today we are going to start group 16 elements, that means oxygen family. Oxygen, sulfur, selenium, tellurium, polonium and livermorium constitute group 16 of the periodic table. This is sometimes known as group of chalcogens. The name is derived from Greek word for brass and points to the association of sulfur and its congeners with copper. Now, congeners are biologically effective drugs or compounds. That means it affects body and brain. Most copper minerals contains either oxygen or sulfur and frequently the other members of the group. Now, simple reason is because they are electronegative elements and they can form multiple bonds. Oxygen, sulfur usually forms two bonds at a time, so they are divalent and electronegative elements. That's why they easily attach with metals. Occurrence: oxygen is most abundant of all the elements on Earth. Oxygen forms about 46.6% by mass of Earth crust. Dry air contains 20.946, that means almost 21% oxygen by volume. However, the abundance of sulfur in the earth crust is only 0.032.1%. Combined sulfur exists primarily as a sulfate such as gypsum, epsom, and barite, and sulfides such as galena, zinc blende, copper pyrite, etc. Traces of sulfur occur in hydrogen sulfide in volcanoes and organic materials such as eggs, proteins, garlic, onion, mustard, hair, and wool contain sulfur. Selenium and tellurium also found as metal selenites and tellurides in sulfide ores. Polonium occurs in nature as a decay product of thorium and uranium minerals. That means when radioactivity obtained from thorium and uranium, it eventually converts into polonium molecules, atoms. Livermorium is a synthetic radioactive element. Its symbol is Lv, atomic number 160, atomic mass 292, and electronic configuration Rn 5f14 6d10 7s2 7p4. And by means synthetic radioactive element, it is not naturally occurring element. Instead, it is made in laboratory. It has been produced only in very small amount and has a very short half-life, only a small fraction of 1 second. That means as soon as we made it, it instantly decays in some simpler atoms. This limits the study of property of Lv. That means we do not have much data about this element because it has very short life and it is not available naturally. So in laboratory, if we made it, within a fraction it will decay in some simpler atoms, so we do not have enough time to study it. That's why, except for livermorium, important atomic and physical properties of the other element of group 16 along with their electronic configurations are mentioned in table 7.6. Some of the atomic, physical and chemical properties and their trends are discussed below. So atomic mass, atomic number, electronic configurations are mentioned. Then we have covalent radiuses. As we move from top to bottom in this group, their radiuses will increase because of increasing orbits. As we can see in oxygen, outermost orbit is number 2, then we have 3, 4, 5 and 6. So as we move from top to bottom, because of increasing principal quantum number, radiuses increases. Then we have ionic radiuses. Now same type of trend will be observed here. If compound forms negative ion, then they will accept electrons and sizes will increase. So as we can see, when oxygen forms O-2 ion, its size will increase. And same trend is observed throughout the case. That means each and every element shows higher ionic radius than the covalent radius, because as we can see here, these radiuses are specifically mentioned for E2 minus ions. Then we have electron gain enthalpies, so it is almost close to each other. Slightly increment, then it will decrease eventually. So because of smaller size of oxygen, usually electron repulsions are high, and that's why electron gain enthalpy of oxygen is comparatively lower than the sulfur, although it is more electronegative than sulfur. Then we have ionization enthalpies. As we move from top to bottom, because of increasing size, metallic characters are also increasing. That's why removal of electron becomes easy. So smaller elements have stronger attraction towards the electron. That's why it is hard to remove the electrons from smaller atoms. So oxygen shows higher ionization enthalpy because of small size and higher electronegativity. But as we move from top to bottom, size increases, electronegativity decreases, and that's why removal of electron becomes easy. So ionization enthalpies decreases. Then we have electronegativity. So as discussed already, because of increasing metallic character, electronegativity decreases. Densities of elements with increasing atomic number, more number of neutrons and protons will be present at the core, and that's why it shows higher density with increasing atomic number. Then melting points, boiling points and common oxidation states of each elements are mentioned. So as we can see, lower number elements shows more negative oxidation states, and higher number elements shows less negative oxidation states and more positive oxidation state because increasing metallic character. So same points are discussed in this description portion. So we are moving towards the next point, physical properties. Some of the physical properties are already mentioned in table 7.6. Oxygen and sulfur are non-metals, selenium and tellurium are metalloids, whereas polonium is metal. Polonium is radioactive and is short-lived, half-life of 13.8 days, and all the other elements exhibit allotropy. That means they will form different type of molecules with same type of atoms. As for example, oxygen forms O2 and O3, that means two different molecules having oxygen atoms only. The melting points and boiling points increases with increasing atomic number down to the group. The large difference between the melting and boiling points of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecule O2, whereas sulfur exists as polyatomic molecule S8. Now in chemical properties, first we will discuss about oxidation states and trend in chemical reactivity. So elements of group 16 exhibit a number of oxidation states, and as mentioned earlier, usually p block element shows alternate oxidation states. So the stability of -2 oxidation state decreases down to the group. Polonium hardly shows -2 oxidation state. Simple reason, because of decreasing electronegativity, elements becomes more and more electropositive. That's why they have less tendency to accept electrons. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2 except in case of OF2, where it shows +2 oxidation state because fluorine is more electronegative than oxygen. Other elements of the group exhibit +2, +4, +6 oxidation state, but +4 and +6 are more common. Sulfur, selenium and tellurium usually shows +4 oxidation state in their compound with oxygen and +6 with fluorine. So higher negative element can give us higher positive oxidation state. The stability of +6 oxidation state decreases down to the group, and stability of +4 oxidation state increases. Just common reason, inert pair effect, we already discussed about it in group 15. Bonding in +4 and +6 oxidation state is primarily covalent because higher oxidation state, that means it has more number of protons in nucleus and less number of electrons in orbits. So it shows stronger attraction towards the electron and it makes covalent bonds. Now just like nitrogen in group 15, oxygen shows anomalous behaviors in group 16. The anomalous behavior of oxygen, like the other members of p block present in the second period, is due to the small size and high electronegativity. And we can add one more thing, absence of d orbital. One typical example of effect of small size and high electronegativity is the presence of strong hydrogen bonding in H2O, which is not found in H2S. That's why water is in liquid state, whereas H2S is gas. The absence of d orbital in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, In case of other elements of the group, valence shell can be explained and covalency exceeds 4. Now in chemical reactivity, first is reactivity with hydrogens. So all the elements of group 16 forms hydride of type H2E, and E is equal to OS, ACTE and PO, that means all the members except the last one. Some property of hydrides are given in table 7.7. Their acidic character increases from H2O to H2TE. Now keep in mind, when we have non-metallic hydrides, they are usually basic in nature, and metallic hydrides are acidic in nature. The increase in acidic character can be explained in terms of decreasing bond enthalpy for the dissociation of He bond down to the group. And why bond dissociation enthalpy decreases? Because as we move down to the group, electronegativity of group members increases. So that means if you have hydrogen which is normally electropositive, it feels stronger attraction towards the electronegative elements. So it will feel stronger attraction towards the top side elements or initial group members. But as we move down to the group, because of increasing metallic character, both hydrogen and our element both have similar type of nature. That's why they repel each other or they attract each other weakly. So they easily gets disconnected, and it is the reason why metal hydrides are acidic. Owing to the decrease in the enthalpy for the dissociation of He bond down to the group, thermal stability of hydrides also decreases from H2O to H2PO. All the hydride except water possesses reducing property, and this characters increases from H2S to H2TE. And properties of hydrides are mentioned in this table. Next is the reactivity towards the oxygen. All the element forms oxides of EO2 and EO3 type, where E is equal to except oxygen remaining elements. Ozone and sulfur dioxide are gases while selenium dioxide is solid. Reducing property of dioxide decreases from SO2 to TiO2. SO2 is reducing while TiO2 is oxidizing agent. Again, keep in mind, just like the hydrides, oxide shows opposite nature. In case of hydride, as we discussed, non-metal hydrides are basic in nature. Then oxides of non-metal will be acidic, and metal hydrides are acidic in nature, and metal oxides will be basic in nature. That's why reducing and oxidizing agent behavior is explained. Besides EO2 type, sulfur, selenium and tellurium also forms EO3 type oxides, SO3, SeO3 and TiO3. Both type of oxides are acidic in nature. Now reason of these oxides being acidic in nature is these elements are usually not as electropositive as the other members or other remaining group elements. That means these are comparatively electronegative elements throughout the group. Only last element is metallic in nature. That's why all of the remaining elements shows basic oxides. Now reason of being acidic oxide is all of the elements mentioned here are almost non-metallic, or either they are semi-metals. Only last element PO or polonium is metallic by nature. So PO oxides will be basic in character and other oxides will be acidic in nature. Next is reactivity towards the halogens. Elements of the group 16 forms a large number of halides from type EX6, EX4 and EX2, where E is an element of group and X is the halogen. Now oxygen, as mentioned earlier, has limitation. It forms only 2 bonds and rarely exceeds it. So here E represents elements except oxygen. The stability of halides decreases in order of F minus Cl minus Br and I. That means F minus halides will be strongest and I minus halides will be weakest. Amongst the hexahalides, hexafluorides are only stable halides. All the hexafluorides are gases in nature and they have octahedral structure. Sulfur hexafluoride is exceptionally stable for steric reasons. So it is a very stable compound. It has octahedral structure and it also increases the covalency of sulfur. And remaining halides cannot form this type of hexahalide because they are not sufficiently electronegative like fluorine. Amongst the tetrafluoride, SF4 is gas, SeF4 is liquid and TeF4 is solid. Those fluorides have sp3d hybridization and thus have trigonal bipyramidal structures, in which one of the equatorial position is occupied by lone pair of electron. Thus the geometry is also regarded as seesaw geometry. Now sp3d, that means we have 1s, 3p and 1de, that means total 5 electron pairs around the central element, let's say sulfur. So we have to arrange these 5 electron pairs as trigonal bipyramidal. So 3 equatorial bonds will be present here, that means like one bond here and one here, placed at the corner of triangle. One electron pair will be like this, perpendicular with this triangle. One electron will be here at the bottom side, perpendicular with this central triangle. So this red dots represents equatorial bond and these blue dots represents, let's say, axial bonds. So one of the equatorial bond will remain as lone pair, that means no element is attached here. Okay, and remaining structure is present, that means let's say here 2 fluorines are present as equatorial bonds and 2 fluorines are present at axial bonds. So as we can see here, we have seesaw type of structure. That means we can rotate this structure at 90-degree angle and you will get this type of structure. Sulfur at the center, this will be one axial bond, this will be second axial bond, and one of the equatorial bond is going behind the plane like this. So one fluorine is going behind and one fluorine is coming out of the plane like this. So we have a seesaw type structure and here is a lone pair. So this is resemble of seesaw type structure. All the elements except oxygen forms dichloride and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalide are dimeric in nature. And examples are S2F2, S2Cl2, S2Br2, Se2Cl2, Se2Br2. These dimeric halides undergo disproportionation as given below. So that means one higher and one lower oxidation state containing product than the reactant. As mentioned, Se2Cl2 give us SeCl4 and Se. That means in Se2Cl2, Se has +1 oxidation state. In SeCl4 it has +4 and in Se it has 0 oxidation state. In next lecture we will start with dioxygen.